In this video, we're going to summarize some of the important topics that we saw in this section 17.1 on parametrized curves. So let's go ahead and read through some of these boxed ideas together. So first of all, in general, in these examples too, we've seen two ways of representing a curve. So those two ways, we call them parametric form. And that means we have equations of the x, y, and z coordinates given to us as functions of t. And then we also need to specify what t is doing. So t is going between a and b. We also, though, saw, as in the preliminary example, vector form for such equations. So that means we're given a vector function, meaning you input a t, output a whole vector, where the components of the vector are given to us as, again, functions of t. So this is just language here and notation, but we're essentially doing the same thing. We're describing a curve C by using an interval of t. And so we can even think of t as a little interval from A to B, where we increase that interval from A to B. All right, so visually, what does this mean? Well, since t goes from A to B, the first point on our curve will look like x of A, y of A, z of A. And then as t increases, so we could say like as we have t1, t2, t3, etc. So as t increases from A to B, we curve out, or we draw out our curve till we get to x of B, y of B, z of B. That is until t equals B. Okay. So now another way we can think about this is, of course, in the vector form. So rather than thinking of these points, we can think of, well, at the start, we get a vector. So that's r of A. And then we get these other vectors, r t of 1, etc. So often we think of parametrized curves as being drawn out in this way, but we can also consider that at any point we have a vector from that origin 0, 0, 0. Right, so now let's look together at some special curves in their parametrization. So first, let's consider the circles in the xy plane. So we did see this in some of the earlier examples in this section, but here we just have it summarized for us, and it's convenient then to reference back to these equations. So here it says the parametric equations for a circle of radius r in the xy plane centered at the point AB and traversed once are given by the following. So if we want to traverse the circle counterclockwise, so that means we're starting going this direction. That's counterclockwise. So similar to how you've seen the unit circle being traced out. Then our coordinates are going to look like x equals a plus r cosine t, y equals b plus r sine of t. So again, we can see that that center is coming up in the a and the b in our equations. And then that radius is the scale that we're multiplying r sine or cosine by. And here we only need to take t goes from 0 to 2 pi. But now if we want to traverse in the opposite direction, notice how the equations change. We now have that we're subtracting the r sine t in the y. And we can make sense of why this should be. So wherever we start, or rather the center, AB, as we start at t equals 0, we're always just going to get a comma 0. But then as t increases, if we have a negative value here, the y value is going to decrease. So say we start here, the y value will decrease first. So our circle will be traversed clockwise. And just a note, as we saw in some of our examples, these equations can be extended into 3 dimensions, which we could do that by adding, say, a fixed z. And there are other ways to do that as well. So now let's look at the parametric equations of lines. So to summarize here, we're going to look at some ways to represent an equation of a line parametrically. But to begin though, let's let V be the vector AI plus BJ plus CK be the vector parallel to the line, a vector rather parallel to the line. And let's let P be the point X naught, Y naught, Z naught, be a point on the line. And we can see this set up in the diagram. So P is here, R is here, R is at the end of some vector V that lies on our line. All right, so there's actually many ways that we could write the equation for this line L. But one particular way we can do it is, we need an equation for each of our coordinates. So we can let X be X naught, our starting value, plus AT. Because as we move in T, we're going to just add A more components to the X each time. So then similarly, Y would look like Y naught plus BT, and Z would look like Z naught plus CT. And so what is happening with T? Well, we have this entire line here that we're parametrizing. So T can be anything between negative infinity to infinity. And in fact, T goes between, if we so want to use that language, negative infinity to infinity. Okay, so that's for this parametric equations for this entire line. But what if instead we only want to parameterize the line segment here from P to R? So that means we only want to describe the line segment P to R. Well, we're going to have a similar setup. So we do need maps for each of our coordinates. And so we're still going to traverse along our line X naught AT plus Y naught BT, and Z is Z naught plus CT. But what's going to be our values of T now? So we don't want to trace across everything. We only want to trace across P to R. Well, notice that when we're at P, T is going to be 0. So we want to start at T equals 0. And then R is the end of the vector V. So when we're at R, T will have just increased by 1. So we'll have T just go between 0 and 1. All right, so finally here, let's look at functions in the XY plane. So that means, just for a visual, we have our X and Y plane, and we have some function f of X. So the output values, Y's, are determined by f of X. So given a curve, Y equals f of X in the XY plane, i.e. X is the independent variable and Y is the dependent variable, the parametric equations for the portion of the curve running from the point A, f of A, and B, f of B are given by, well, X is just our T value, and then Y is the output of F. And here, since we're starting at X equals A and ending at X equals B, that would mean T goes from A to B. And of course, as in the previous examples, these formulas can easily be extended to give equations of functions of Y, or like we saw in example 4, or curves in 3-dimension or 3-space by just including a third coordinate. All right, well, great work going through this final summary of parametric curves in section 17.1.